In this video, we shall take a look at some further properties of the PGF. The properties that we have already seen in the last video were all kind of real analytic properties where we dealt with it just as a function. Now we shall see its probabilistic properties, something that relates the PGF with the underlying random variable and its distribution. So we have seen how to construct xi from pi's. Now this one allows you to do the other way around. If I give you the xi function, then you can recover all your pi's. So what you do is you keep on differentiating xi again and again at 0. Remember, it is always defined from -1 to 1. So 0 is at the center. So you can differentiate. Differentiate it I times, evaluate it at 0 and divide by I factorial. You will get your pi. Now that is pretty easy to see. I have this definition. I have just expanded this out. Now, suppose I take I equal to 0, then you do not need to do any differentiation at all. Just set t equal to 0 and you get p0. So it is xi 0, which means no derivative, just the function itself, evaluated at 0 divided by 0 factorial. Okay, I differentiate it once, then this dies, and we are left with this, and whatever the thing is, it is p times something. I do not care what it is, but all these things will have at least some t in it that I have taken common. So when you evaluate this at 0, this entire thing dies and you are left with p1. So it is p1 and you are dividing by 1 factorial, which is 1. Okay, let's do it one more step. I have written it out once again. Now in order to arrive at p2, I have to differentiate it twice. So when I differentiate it for the first time, I kill this. When I differentiate it for the second time, I kill this. Now for the first differentiation, it becomes 2p2t. For the second differentiation, this once comes here, so it is basically 2 times 1, p2. All the remaining things will have at least one copy of t in it. So when I put t equal to 0, they die. They are already dead. So you are left with 2 factorial times p2. If you differentiate once again, you will get 3 factorial times p3 and so on. Hence you get this result. Now this result is also like a real analysis result, but it has an interesting probabilistic interpretation. Remember, these pi's are all the probabilities. So I can say if I know the probability generating functions, I can generate all the probabilities out of it. That is precisely why it is called probability generating function. And this can be written in a probabilistic way like PGF characterizes the distribution. By this I mean that suppose I have got two random variables x and y, both taking only non-negative integer values, and I know that both of them has the same PGF xi t. In that case, I can say immediately that x and y must have the same distributions, because I will use this prescription and I will get the same set of pi's for x as well as for y. Also observe that all that I care is that all the derivatives must match at 0, and for this all that I really need is they must have PGFs that match only over some neighborhood of 0, some minus epsilon to plus epsilon. Immediately all the derivatives must match at 0. So even if I say x and y have got, say, PGFs, one of them has PGF xi t, the other has PGF eta t, but I have this result that xi t equals eta t. I do not say for all values, but at least for all t in some minus epsilon to plus epsilon. Immediately I can say that both of them must have the same distribution. In particular, xi t must be equal to eta t everywhere that they are defined, and all the pi's are same for both x and y. So PGF characterizes the distribution. This result holds only for random variables taking non-negative integer values. Now I shall give you your exercises. This is the background information. PIs are related with X in this way, and this is the definition. Now the exercises, I call it 6 because it is actually one of those properties. So it is basically property 6, whose proof I leave as an exercise. Show that expected value of X is xi prime 1. So what you do is you just differentiate term by term and you plug the value 1 and you will immediately get the result. Now there's a little problem here. You might say, I only know that this is guaranteed to exist from -1 to 1. So it is only on one side of 1. But if I have to differentiate it, then I have to differentiate on both sides of 1. Well, here we have the understanding that I am only working with the left hand limit. The left hand derivative at 1. And I can also give you that assumption that you can assume that expected value of X here is finite. This is a non-negative random variable, so it can never become infinite or do oscillation and things like that. So I tell you that it exists finitely. Now once you do this, you can generalize this very easily to higher order stuff like this. So here I compute this quantity x times x minus 1, etc. There are k many terms here. X minus k plus 1. Expectation of that will be very much like this. For k equal to 1, you get back this. The kth derivative evaluated at 1. So now I am not evaluating it at 0. In these two examples, in these two exercises, I am evaluating the derivative at 1. Again, I am allowing you to assume that this is finite. That is actually not very essential. Even if it is infinite, this will also turn out to be infinite. And as before, you consider only the left hand derivative at 1. Now the last exercise is the easiest of them all. Show that the PGF can be thought of as expected value of t to the power x. Now what values of t I am talking about? Again, any value of t for which xi t is well defined. So in particular, let's work with -1 to 1. I know that no problem will occur for this. This is just nothing. You just write down the expectation, you will find you are writing this. So it is very trivial. But this one is slightly non-trivial, and this is just a special case of that.